This is Dr. Brothers, and we are back with another video. This is going to be for Lecture 8, and we are going to introduce the concept of the Fourier transform in this lecture. So, let's just go back a step and look at the Fourier series. Let's see. I'm going to zoom in just a bit. So let's go back just a little bit and look at the Fourier series. So if we look at the Fourier series, we have the following. A of k is equal to 1 divided by t naught, the integral from negative t naught divided by 2 to t naught divided by 2 of x of t times the exponential of negative j 2 pi over t naught kt dt. And we also have x of t is equal to the summation from k is equal to negative infinity to infinity of a of k e to the j 2 pi t naught kt. Alright, so these are the Fourier series equations. One thing to note about these equations that they are for a periodic signal over the period t naught. So every t naught, the same signal will repeat. So this brings up an interesting question. What happens if we expand that period of t naught and just keep expanding it until it is infinitely long? So, in order to do this derivation, the first thing that we're going to do is take this first equation and we're going to multiply both sides by t naught. So that gives us t naught a of k. Let me put a section heading here. This is going to be, assume t naught is very large. So t naught a of k is equal to, that multiplies this over to the other side. So now we have the integral from negative t naught divided by 2, t naught divided by 2, x of t e to the negative j 2 pi over t naught kt dt. Okay, so we're also going to modify this guy before we begin, and we're just going to move variables around just a little bit. So we're going to say x of t is going to be equal to 1 over 2 pi summation from k is equal to negative infinity up to infinity of t naught a of k e to the j 2 pi kt divided by t naught, and then we're going to reintroduce the 2 pi divided by t naught. So if you compare this equation that we just wrote at the bottom, we introduced a t naught in the numerator and denominator, and we introduced a 2 pi in the numerator and denominator. So all we did was, multiply by 1. So these are the same equation. We just introduce some variables so we can keep track of things as we move through. So I'm not going to go through a vigorous mathematical derivation. What the textbook actually says, it says, now wave your hands vigorously while letting omega turn into the limit of t naught approaching infinity. So we're going to make some substitutions. We're going to say that omega is going to be equal to the limit of t naught approaching infinity. So we're making this period very, very large, of 2 pi k divided by t naught. We're also going to say that d omega is going to be equal to the limit of t naught approaching infinity, and this is going to be 2 pi divided by t naught, and we're going to do one more, and that is x of j omega is going to be equal to the limit t naught approaching infinity of t naught a of k. Okay, so we just defined some variables here. As t naught approaches infinity, we're just going to call this term omega. Now, if you think about what's happening, as t naught gets very large, this gets very small, and this is basically the harmonics. So we are shrinking the distance between the harmonics, which are denoted as k. So that's making the period longer and longer, but the distance between each one of the harmonics is actually getting smaller because it's dividing by t naught. And so omega now becomes a continuous time version of the harmonics. So as they get smaller and smaller and smaller and smaller and closer and closer and closer together, it actually becomes a continuous value as t naught goes to infinity. D omega, same concept. And then the substitution that we're going to make, x of j omega, this is capital X. So it's hard to see the difference, so I'm going to underline this to make sure that you understand that this is a lowercase x of t and this is a capital x of j omega. So x of j omega is the Fourier transform, and this is the magnitudes of the harmonics as t naught gets very, very, very large. So there's going to be a larger and larger and larger period for these, and so it's going to turn into, again, a continuous time covering all values. So if we take these and substitute them in to these equations, wow, I really substitute. Yeah, I think I spelled that right. Okay, so if we do that substitution, that brings some new equations. X capital j omega is going to be equal to the integral from negative infinity to infinity. Originally this was negative t naught divided by 2 to t naught divided by 2. We're moving t naught to infinity, so that becomes infinity, of x of t, which is still in that same e to the negative j. Now we have 2 pi divided by t naught, 2 pi k divided by t naught. So 2 pi k divided by t naught we're going to replace with omega. t, and then this is dt. In the other equation, we have x of t is going to be equal to 1 over 2 pi integral. So originally it was the summation because k was integer values. However, as we're moving t naught to infinity, that actually decreases the distance between each k value until it becomes a uniform distribution of values. Like I said, we're not doing a vigorous mathematical proof, just the concept is what we're looking for. So x naught of, or t naught of ak, t naught of ak. So we're going to do this substitution with the capital x of j omega. And then again we have e to the j omega t. So 2 pi t naught, 2 pi divided by t naught times k gets replaced with omega. And then the last term that we have is 2 pi over t naught. 2 pi over t naught is getting replaced with d omega. So these are the resulting equations, and these are the Fourier transform pairs. Okay. This is an important concept. What we're saying, as we moved t naught out to a value of infinity, we took away the repetition, and in that the a of k's became, instead of integer spaces, those spaces became delta omega away. And so when we move those down to the delta omega, now the k term turns into a continuous omega term. So the same theory that we were using for the Fourier series, where we were finding the values of the harmonics that resulted from this integral, we now apply that to find the Fourier transform. The Fourier transform is one of the most powerful tools that we have in signal processing, and it allows us to transform back and forth between the frequency domain, which is capital X of j omega, and the time domain, which is x of t. So we will spend a lot of time looking at these more. So let's look at a quick example. So example. So x of j omega, we're going to find that for, okay, so let's say find x of j omega for x of t is equal to e to the negative at u of t. This is a decaying exponential. This is something that we have defined before. This you are currently seeing on the homework assignment, where it is e to the negative 1 over rc t. So same equation. We're going to look at this in the Fourier transform region. So solution. Sorry, I did not write this in the given find solution format. This should be the given. So x of j omega, we're going to start out by writing the integral for that. So the Fourier transform integral integral from negative infinity to infinity of x of t, which is e to the negative at, u of t, times e to the minus j omega t. Now we can see something right away. This integral is 0 for t is less than 0. So we can rewrite this and change the limits. We can say the integral from 0 to infinity of e to the negative at. And now, over this region, u of t is always 1, so we can just leave it out and say e to the negative j omega t. We can combine these two, the integral from 0 to infinity of e, and when you have these exponents, you can add the exponents. So this becomes the negative of the quantity a plus j omega t, and I forgot all my dt's, dt, dt, dt. Okay, so now we have an integral, and we can look this up in the integral tables. When we do, we find out that this is 1 divided by negative a plus j omega times the original exponential of negative a plus j omega of t evaluated from 0 to infinity, which is equal to 1 divided by a plus j omega. So this is the frequency equation for this guy. So what does this mean? X of j omega. This is capital. I'm just underlining that to show that it's capital, in case you can't tell with my handwriting. So that's the answer. Now, let's take this just one step further and say that we want to see what so in the homework, I'm trying to figure out how to say this without giving too much away. You're asked to find the maximum output of the cross correlation. The cross correlation shows the relationship between the input and the output. So it shows how the different amplitudes are being affected. So let's look at the amplitude of this guy and see what kind of an equation that gives us. So what we want to do is find the magnitude of x of j omega. And so we can say that the magnitude of h or x of j omega squared is going to be equal to h of j omega times h complex conjugate j omega. This is just an easy trick to find the magnitude. 1 divided by a plus j omega times 1 divided by a minus j omega. This is the complex conjugate in the second denominator. When we do this multiplication out, this is equal to 1 divided by a squared plus omega squared. If we want to find just the magnitude, we need to take the square root of this. So the magnitude of x of j omega is equal to the square root of 1 divided by a squared plus omega squared. So what does this look like? You can see that as omega gets larger, it becomes the dominant term in the denominator, and as omega tends towards infinity, this will become 0. So we'll leave the rest of this discussion for after we have done the homework, and we'll continue to discuss this in the next class period. But just think about this. This is the same type of equation that you have applied on your homework. And so as omega gets larger, this is going to tend towards infinity. It might be a good idea to plot this and see what it looks like for different values of omega and see how that compares to your homework values that you're getting for the cross correlation. This is the introduction to the Fourier transform. There's going to be one more quick video. I'm actually going to have a video from one of the guys who has written a book on signals and systems that discusses the Fourier transform properties. He goes through the Fourier transform properties and has a very nice video on that, so I'm going to give that as the link to the final video for this lecture.